Looks like we're just about there, folks. Welcome back, everyone. Well, I hope midterm weeks has not been too brutal for everyone, and we're all getting through it. But if you're a little tired today, I totally understand. I'm pretty tired too, but we're getting through it. Excuse me. For the announcements, really, it's just mostly centered on our exam two, which is going to be next Monday. Like we mentioned before, it's going to be just over those sections there. But I'd say one thing to emphasize definitely, when you're studying for an exam, you are allowed to bring on the real exam an 8.5 by 11-inch page of notes. Starting there by compiling your notes is probably the best strategy for your first step on studying. That way, if you have your notes ready to go and then start looking at study problems, you'll have your notes, let's pretend this is the notes, you'll have your notes already set. You'll be able to orient yourself where all your information is. You'll be able to decide also, did I even need that formula? Should I put something in if I missed it? That kind of stuff. So having your page of notes ready to go is extremely helpful for studying because you want to use it as you're studying your questions. Other reminder is it is an open calculator exam, and there'll be some problems where we are going to approximate a couple things. So don't forget to bring your calculator. I do have spares, but you want to bring the calculator you're used to using, not just a random TI-30XA. That's almost like a punishment. Aside from that, any questions at all, folks, about the upcoming exam two? Okay. If you're studying on this exam and you have any questions over the weekend, please don't hesitate to email. I'm not on my email all day, but I check it every single morning. And when I check it in the morning, I just go through the backlog of every email I've got. So if you're sending me a bunch of questions, even at 3 a.m. when you're studying, that's totally fine. I'll get to them in the morning. So don't hesitate to write. Well, aside from that, we're moving forward in the section 11.1. We're nearly done with that section. And we're going to go next to section 11.2, working with series. We'll take section 11.2 a little bit slow because we're connecting the dots on what we did in section 11.1, sequences, and finding out what's new in section 11.2 with the series. Well, I think that's my entire spiel for the announcements. Any questions at all, folks, before we go back to 11.1? Okay, so let me clear these out. And in 11.1, we ended up right around here. First example, that's a good one to take another look at because it's definitely kind of a weird one. We're dealing with the factorial function. And the strategy for these things when they come up is we just need to start canceling. Best way to do that is expand out one of them. We went for the one with the larger value, the +3 being the larger value. We expanded it out in this way. And the strategy for that is n factorial always goes this way. N times n minus 1 times n minus 2 and so on. But if you like, you can write n factorial as n times n minus 1, and then just stop here with n minus 2 factorial, because n minus 2 factorial is all of the rest of it. So it's an algebraically correct thing to do. So when we went to write out 2n plus 3 as 2n plus 3, and then stop at 2n plus 2, is because we had an intention to do that cancellation right there. Again, pretty weird problem. There's one like this in the homework as well. And it's actually more important than it looks like. This kind of stuff comes back, factorial functions, when we're dealing with power series later on. It's kind of mysterious how, but the reason is it's all because of taking higher and higher order derivatives. It just emerges in a formula. Next thing we're going to take a look at is just a couple more sequences. So for each one of these, we're determining if the sequence converges or diverges. Diverging means it's not settling down on a finite number. So either it's oscillating between 5 and -5 for all time, or maybe it's blowing up to positive infinity or negative infinity, or maybe half the terms are going to positive infinity, the other half going to negative infinity. Lots of crazy things that can happen here. So now for this one, we want to decide what's going to happen to this as a limit. But really it was about properties of logarithms. If you're subtracting logarithms like this, it can turn into the natural log of n plus 1 divided by n. And if you want to, this is not a bad one to do just a little bit more algebra on. That's the same as the natural log of 1 plus 1 over n So to determine the convergence or divergence of that sequence, we take the limit as n goes to infinity of the nth term an. But that then by substitution turns into the limit as n goes to infinity of the natural log 1 plus 1 over n. And now we have continuity working in our favor. The natural logarithm is continuous as we go from 0 up to infinity, not including 0. Because of continuity, the limit operator does this. Goes inside the function, affecting the 1 plus 1 over n. So now when we go to take this limit, 1 over n goes to 0 by one of our prior theorems up in the notes. This right here by the red dot goes to 0 because the numerator is constant, but the denominator is growing without bound. So that's just my little shorthand on the notes. Whenever something just gets eliminated through a limit like this, converges to 0, it leaves behind nothing but the natural log of 1, which is 0. So when these terms get larger and larger, they are approaching the value of 0. And you can get as close to 0 as you like by making n sufficiently large. So this one converges. Any questions, folks, with running through that one? Okay, that leaves just one last one on the notes here today. The sequence when it's sine n times pi over 2. Kind of formatted weird. If you'd like, you could just visualize this as sine n pi over 2 if you prefer. I guess I wrote it this way just mainly to signify the index n for the nth term is just highlighted there. So either way we look at it, anyone have any guesses on what could happen to this sequence? Does this look like it's convergent or divergent? It's a weird one because if we did take the limit of it right now and wrote out limit.
Can I say it converges on 0?
Turns
No?
out this one doesn't converge on 0, but you know what? With one small change, if n is in the denominator, you would be right, because then the thing inside here is getting closer and closer to 0, and sine of 0 is 0. So because of the placement of n is really in the numerator, turns out this one does not converge to 0. It's kind of a weird one. Any other questions or comments with it so far? Okay, so visualizing this a little bit more, if we were to try to resolve this by just taking the limit of it as it stands, it would look like this. Limit as n goes to infinity of sine n pi over 2. But then we don't really have any limit law to help us with that. Not whatsoever. And it's not as if you can go and write sine infinity pi over 2. It not only doesn't help us, it also has no meaning whatsoever. Yeah, go ahead. This one is oscillating. Good call. So that means this limit right here does not exist. Which means the sequence an diverges. So if you see something really odd like this thing, or formatted differently like this, a good strategy is just to do this step. Get some intuition of what the sequence even looks like. You could write an, as n goes from 1 to infinity, is this sequence. Plug 1 in there to start it off. That's sine of pi over 2, which is a 1. Next, you plug in 2. That's sine pi, which is 0. If you plug in 3, sine of 3 pi over 2 is negative 1. Plug in a 4, that's going to be sine 2 pi, it's 0. And the whole pattern just keeps on repeating. 1, 0, negative 1, 0, 1, 0, negative 1, 0, dot, dot, dot. And so this is what's going on. We can't even really take the limit of this thing whatsoever. There's no limit law that helps us. The limit plainly doesn't exist because that pattern repeats forever. So we can say it diverges because the terms oscillate. Let's spell that correctly. Oscillate, let me know if I'm spelling that wrong. Seems right. Let's go with oscillate that way. Between 1, 0, -1, endlessly. Or forever, you could say. If that ever happens, the limit doesn't exist because the values of these terms are not actually settling down to anything. They're just always oscillating. And so that's a divergent sequence there. Well, any questions, folks, with getting through that last one? Kind of the trickiest one of the whole set. Okay, well, we did it, folks. This is the whole section on sequences. What we're doing next is converting over to dealing with series. Any other questions about this material before we jump over? Okay, let's move over to that next section then. I put like a million revisions on this section, so sorry about that. I'm going to try to proofread these things a little bit better before I release them. A lot of the revisions were, I was just kind of going back and forth between which problems I wanted to ask. So I changed these out to make them a little bit more interesting. I had a list of where everything was diverging except for that last one, so a little bit more variety. I also switched out this problem right here below. This was a really tricky theorem, the test for divergence, so I want to give a little bit more extra content about the easy way to misuse theorem 6. So those were some of the major edits there. But let's start at the top then and get working with this content. So the way a series works is, we've hinted at it before, what we do is we take a sequence, say that one just for a particular example, and a series forms a sum using every single term of the sequence. So in order to form a series, we'd start looking at the sequence of partial sums Sn. The sequence of partial sums are very valuable for us because if we just write down something like this, summation as I goes from 1, let's go with index n rather, sorry, as n goes from 1 to infinity of 1 over n, what we're saying is we're going to take 1 plus, put in an index of 2, a half, plus a third, plus a fourth, plus, and keep on going until you get plus the nth term of the sequence, which is 1 over n, but then you just never stop. So we want to determine, does this have an actual finite value when we add together infinitely many terms? But the way we decide that is, we don't look at the full summation here that goes off to infinitely many terms. We look at the partial sums first, because that's something we can get a handle on. No one can physically add infinitely many terms, but we can look at a sequence of partial sums. So S1 being A1 means, for our problem, S1 is this. S2 being A1 plus A2 means S2 are the first two terms, and so on. S3 is the first three terms going that way. We wonder if we keep on doing these things, go up to the nth term, Sn is up to A1 through An. If we keep on labeling these things, we'll say that this is equal to the limit as n goes to infinity of the summation as I goes from 1 to n of Sn. So what we're conveying here is, if this total sum really has a limit, then it should be found by finding the limit of the partial sums. Sn is going up here, this many terms, but when we take the limit as n gets higher and higher, it means we're involving more and more terms altogether in the limit. So pictorially, that's what's going on with series, and it's a lot of moving parts. So again, we're going to break this down carefully and see how it all comes together with this one example right here. Now, if you already read the book in section 11.2, good on you, that's pretty awesome. There's kind of a weird thing that happens with this sequence. And in fact, this sequence, 1 over n, is so spectacularly abnormal for what your expectations might be, it has a name. When we put it in a series, the summation from n equals 1 to infinity of 1 over n is the harmonic series. It's rare for a series to have a specific name, and this is one of them, kind of unusual. So in breaking down this problem, first thing we're going to do is determine if an converges or diverges. Part A is a question about the sequence. So what we do for this one is take the limit as n goes to infinity of an. So this is a section 11.1 question on sequences. And when it came to sequences, those are nice. All you're doing is taking a limit of something. Our an, the nth term is 1 over n for the sequence. So we're taking the limit as n goes to infinity of 1 over n. And we've seen that limit before. That was the first limit we did in section 11.1. That limit is 0 in total. The terms of this sequence get closer and closer to 0 as the index n gets larger and larger. Well, any questions, folks, with this one here? I almost forgot. I want to write converges. Okay, so now if we're thinking about the harmonic series, we're going to kind of redo what we did in section 11.1. To determine if this converges or diverges, you have to go to the sequence of partial sums first and analyze those. So let's take a look at S1. Let's calculate these from scratch. I have a couple homework questions where you're doing just that. We want the first 8 terms of the sequence of partial sums correct to 4 decimal places. So that sounds like a calculator job. Let's get one going. So for the first term, we'll call it S1, which is equal to A1, and A1 itself is just going to be 1 over 1, which is equal to 1. So not too bad, that one's done. For the second term, S2, we take A1 plus A2, but you can speed this up. You don't necessarily want to take 1 plus A2, which is a half. Just take the prior value, A1, which is 1, plus A2, which is a half. And now we've got 1.5. So any questions so far, folks, on going down the line of this sequence of partial sums? Okay, so S3, certainly it's A1 plus A2 plus A3. But if you think in these terms, S3 is nothing but the prior sum S2 plus the new term. That just saves us a little bit of time if we think in those lines. S3 is going to be equal to S2 plus A3. So S2 is A1 plus A2, and we calculated that to be 1.5. A3 is a third, so plus a third. At this stage, we might as well really use that calculator. So we have 1.5 plus 1/3. So that comes out as 1.8333. Next, for S4, I think we can fit it down here maybe. Instead of writing them all out, it's really not too bad to see how it goes. You just add the very next term, A4. A4 would come up here, you're plugging in a fourth, so plus 1/4. And that's our next term, 2.0833. And just about there, here's S5 coming in next. For S5, we're adding in 1/5. So plus a fifth, 2.2833. S6, just as fun as the last one, go into the calculator, add 1/6, so it's now 2.45, that's kind of nice. S7, as we're calculating these all out, thinking along the lines of, does this look like the sequence of partial sums converges or diverges? Let's take a look if we add a 7, how much it changes. Well, it changes, well, by a 7, and we get the new value, 2.5929 upon rounding. And here's the last term of the sequence of partial sums. Here we're adding in 1/8. So plus, scroll all the way to the right, 1/8, and we have a 2.7179. So let's throw that in, 2.7179. So we've calculated the first 8 terms of the sequence of partial sums. These are correct to 4 decimal places. We know that the original sequence converges to 0. And so for the sequence of partial sums, would you say this converges to a number or diverges? Anyone happen to know or have an inkling one way or another?
It does look like it's slowing down.
I agree with you. Yeah, absolutely. That would hint towards convergence. Yeah, go ahead. Awesome. You know what? If I didn't read the book, I would in the favor of what you're all saying. And it does say, does it appear that the series converges or diverges? So we're just answering this qualitatively based on 8 terms. So I would agree with folks. It does appear it converges by calculating the first 8 terms. But there's a bit of a struggle with this one, or extra drama. It turns out that there's a lot more going on with this. We're adding terms of 1 over n. So we added 1 over 8 to get S8. Adding 1 over 9, we're not adding too much on each additional step. But it turns out we are actually adding enough for divergence, which is a total surprise. It's not easy to see it this way. And our author of our text gives a proof that this thing really does diverge, which is kind of hard to read. We're going to give another proof in section 11.3 when we have something called the integral test. We'll use an improper integral of type 1 on domain 0 to infinity to actually prove this really is a divergent sequence. It's, again, a total surprise. So let's add just a little bit more here. This is where the exercise would end. Let's put a border here and say, in fact, the sequence Sn diverges. It's just not easy to see that. We'll do our own demonstration to show how it could be plausible with numerical values. But this means the series, when we say series, it means we're going this way. The summation, as n goes from 1 to infinity, of an, we plug in the sequence. So n goes from 1 to infinity, summation 1 over n, diverges. So let's get an extra visualization on that because, again, this sequence is not just your random sequence. It has a name. It's called the harmonic series, or excuse me, harmonic sequence. Let's just say that again. Harmonic sequence. So this is an important one. We're going to do just another demonstration to see if this is really plausible. Again, it's hard to tell just by calculating up to S8. First, any questions at all, folks, with dealing with this sequence of partial sums? Okay, so best way for us to visualize this, not really giving a proof, but just trying to make this more plausible before we actually prove it ourselves in section 1.3. Again, the author does give a proof in section 11.2, but it's kind of a difficult one. I would understand if you skimmed through it. So for us, we'll use Excel. This is no proof at all, but we're just looking if we have numerical evidence of any kind. And once I get this thing to move over, there we go. First thing we plug in here is the sequence. We're just looking for where that's indicated. Here it is. We'll plug in the sequence 1 over n. I guess we need to index n first. Then there'll be an. Then the sequence of partial sums Sn. So we'll put in 1 to get it started, then plus 1 here. And we calculate up to 8 terms. So let's see what happens when we go to 16 of them. I always forget that I have to go one further. There you go, 16 of them for real. Now the sequence is this one, so we'll go equals 1. I messed up already. Let me try again. It equals 1 divided by the index n. The index n is to the left, so you just left arrow and get that value there. So now we have the terms of the sequence. And we do know this goes to 0. A 16th is pretty small, for example. So that validates or gives numerical evidence that that's true. But now for the sequence of partial sums, here's what we do. S1 should be A1. So on my sheet, I just go equals to the left. That's A1 there. S2 is A1 plus A2. So on this sheet here, you'll go equals. Well, that's A1 right there, the prior sum, plus A2 is to the left, 0.5. And that pattern that we just took conveys all the way down. So you could just take this and you get the right values. See, for example, here is S3, and we did match up with 1.8333. So plotting these all together, or just looking at what we have numerically so far, compare this with the 8th term of the sequence. We got up to 7, and maybe it kind of looked like it would maybe converge to a 3 or something, right? Because we're adding small quantities around this. At 9, we're adding a 0.1 repeating, then a 0.1, but in fact, goes right past 3. So if this thing really does diverge, we've got to find a way to get it past a 4, for example. So let's see if we can make that happen. Let's take this part of the sheet and just drag it down. Now we're up to the 54th term. 1 over 54 is this quantity, and the partial sum is now 4.57. So again, that's not evidence that it diverges. If it really diverges, you have to exceed 5, for example. But look how slowly this happens. We keep on going with this experiment. Let's go to, say, 382 terms. We've exceeded 5, and now we're at 6.52. To try to exceed 7, this is where it starts to get really wild. Let's go to, say, the 1,000 different terms, or, well, not quite 1,000. We've exceeded 7, and in fact, this game could go on forever. You could pick any large number, maybe 1,000,000, and I could come up with the right index. It's going to be more than 1,000,000 by quite a lot, but we can find that index so that the partial sum exceeds any finite large number you come up with. So that's actually very remarkable. The harmonic series does this, and it's like a borderline case. If you put a power here that's higher than 1, like a 1.1, convergence. 1.000001, convergence again. That's kind of remarkable. The power 1 here is
Can you show that real quick in Excel?
For the 1.1?
Yeah, if we were to increase n to like 1.001 or something.
Kind of a fun experiment. Let's give that a try. So for our an, we have to modify that power, right? It's going to be 1 over n, so that's the index there. Let me try again. 1 divided by n, but then we give it a power. Let me make sure my order of operations are right. Just going to put in extra parentheses for safety. So there's the index. It has a power of 1 by default, matching this up. Let's give it a power of 1.001, something ridiculous like you said. Maybe let's back off to this one, just so that we're not going down to, say, like row 30,000 to make sure it's working out. So starting off with that power, double click this and it updates the whole sheet. And then this one is already configured to give the partial sum for whatever you have here on the index. So now with a power of 1.01, let's see what it looks like at the bottom of the sheet. We get to 7.340966, And let's see if we can make that exceed an 8. Let's get way, way down there. We did exceed 8 on that thing. See if we can exceed a 9. Eventually, this one truly does converge. This will turn into the P-series test, but that's an interesting thing to try to demonstrate. So we're seeing we're going to exceed a 9, and oh my goodness, we sure did. So it looks like this one keeps on getting larger, but this one really is a convergent one. This is maybe just the side effect of trying to use Excel to prove things. It's not an effective system. Let's see how far this can really get going. There's probably a better way to copy this way down to the bottom of the sheet. I bet you there's a shortcut.
What about the A6922 at the top left?
Sorry, where were we looking at?
Right above the like A in the left row columns. Just right above that. Here's that C1.
Oh, interesting. So
Then type like A, whatever.
I'm not actually sure what that does, to be completely honest, huh? Oh, it was just saying the cell I was at.
Okay.
Oh, yeah, I'm not too sure either. But you know what is kind of interesting? This didn't get up too high. Let's do one more try with this and see if we can get it to exceed 10. Again, this is just numerical evidence. This is by no means a mathematical proof. We'll give a better proof of these facts in section 1.3 with the integral test. If we really drag this down, and we got to, well, we're not exceeding 10 on this thing, it looks like. It's kind of remarkable. But again, there is limitations to doing it all this way. Where all this is coming together is on these notes right here. The convergence and divergence flow chart is just going to move down on Moodle as we go to each new section. And we're looking at a P-series, and convergence, or excuse me, the test for divergence is the first one. The P-series right here looks like this, 1 over to the power of P, moving over to, sorry, trying to zoom out on this thing. Guess I'll use that control. So our sequence is 1 over n to power P. If n is greater than or equal to 1, and if P is greater than 1, then we have convergence. So that's what we're saying over here by putting in something kind of strange, a power of 1.01 on every one of these. Power is greater than 1 for convergence. Hard to see on the Excel sheet, but P is not greater than 1. If it's less than or equal to 1, we have divergence. And that's this one right here, where it's exactly 1. So the harmonic series is the borderline case between convergence divergence. Sorry, this was kind of fun. It wasn't easy to show that that's really going on just by Excel. So we'll try to work a little bit harder when we're in further sections. But other questions at the moment, folks? Thinking about the harmonic series?
Can you remind me why n is only an integer? Like in the past, n has been like kind of like a series, like an infinite range of numbers, right? And we're just going 1, 2, 3, 4.
Let me see here.
Is that what makes the sequence? It makes it a sequence.
That's what makes the series, yeah. To define a series, you have to start off with a sequence, and the sequence itself is only on the integer values. But there's a larger question there for sure as well of why do we care about just integer valued functions like these, tying them into series? So for that larger question, it has all to do with things about the derivative. When we go to write out a power series, we're going to do something along these lines. We write out something like f of 0 plus f prime of 0 plus f double prime of 0 divided by 2 factorial plus f triple prime of 0 divided by 3 factorial and so on. So this is kind of our target for everything in chapter 11, developing these kinds of statements here. And all of these things are based off integer values for no derivative, first derivative, second derivative, third derivative, and so on. So that's the actual deeper connection of why everything is an integer all of a sudden when we're normally dealing with continuous things. Does that make sense there for that kind of question there?
It does. I guess I'm having a hard time grasping how we went from limits of something approaches infinity converging, and then when we do it as as a series, we end up converging, or or having opposite, counterintuitive results.
Yeah, this one is extremely counterintuitive. So the kind of thought about this one is for a different demonstration is if it's 1 over n, your power is exactly at a 1, and anything less than 1 is automatic divergence. But if we made the power something like this, power 2. So now with the power 2, we're thinking of an n squared right there. This one is totally convergent. Well, so was it when it was a power of 1.01, but this is a little bit easier to demonstrate. Let's make this come down. And looking at the values, notice this is converging very, very surely by just looking at the integer values here. We go way down the sheet. Recall we're at 1.6437 and some change. At the very bottom of the sheet with 12,000 terms all added together, we're at about the same sum. So the thing that's really counterintuitive is if it's 1 over n squared, as a sequence, that right there goes to 0 very, very rapidly. But if it's 1 over n, it does go to 0, but it goes to 0 so slowly that we get divergence on this thing. Yeah, go ahead.
With that, with our at 1.01, kind of the summation for it, and it stopped at about 17.
Oh, wow. That's kind of awesome. So at 1.01 for the power, 17-ish is what you're getting. That's kind of cool. Or maybe another thought to think about this one, because again, it's an important series and it's so counterintuitive. This one diverging has another connection. It's way over here, way back here. The improper integrals. In the improper integrals, we have a theorem that goes this way. Eventually, there it is. This theorem says that integral right here, 1 over x to the power of p, is convergent if and only if your power is positive. Let's plot that one out. That one's a little bit easier to demonstrate rather than dealing with the sequences in series, because this is all continuous stuff now. So if we go y equals 1 over x to the power of 2, for example, we have some really fast convergence, and it turns out this improper integral of 1 over x squared converges to a finite area. But if p is less than or equal to 1, that whole integral diverges. This is connecting to the harmonic series right again, because 1 over x to the power p reminds us of 1 over n to a power p. Here the power is 1. So if we put in a power of 1 on this function, here's the change. It's kind of hard to see. Let me see if I can zoom in on this just a bit more. If it's power 1, the area looks like this. We bump up the power to 2. Well, maybe if I put the red dot here, it'd be easier to see. Okay, maybe focus on the red dot. At power 1, the area under the curve is actually substantial. It diverges to infinity. But at power 2, the curve goes to the 0 axis so fast that this is actually finite area for convergence. Same thing is happening right over here. At power 1, this is the borderline case where the terms are actually large enough, even though the limit is 0, that if you try to just brute force add them all together, it will diverge. It's not going to 0 fast enough in this one case. And the harmonic series is the borderline case between convergence and divergence. Well, other questions about that so far, folks? Okay, so lots of weird things going on with sequences and series. But what we want to focus on next is a little bit more on what makes a sequence converge. Or excuse me, let me say that again. It's unfortunate that saying sequence and series is so very similar in our minds. I'll try to be really careful between the two. We want to focus very carefully on what makes a series converge. A series is written out this way, but those are just symbols when you go to write out. That's hard to highlight. Let me just use a highlighter. That's what a series is. You're taking some sequence, whatever it could be, whether it converges or diverges, and you're attempting to add up all of the terms at once. This is just a symbol to represent the series, but if the series converges, it means this thing right here, which is a sequence of partial sums, is what converges. The limit as n goes to infinity of that sequence is convergent. If that limit exists, we will say the series converges. But if this actually goes off to infinity, like the harmonic series, we'll say that that series here is divergent instead. So our purpose here on example 2 is to just kind of investigate these definitions a little bit more closely. Sequences are pretty interesting, but once you have sequences together with series, it kind of muddies the water. So we're being careful at first going through this. Any questions, folks, with the definition of a convergent series? Okay, so down below, we're determining if that series converges or diverges. If it converges, we'd be able to say this. It's equal to the limit as n goes to infinity of the summation as I is just an index, not a complex number. I goes from 1 to infinity of an. Oh, hang on, I did make a mistake there. As I goes from 1 to n of an. So this whole thing right here is just another way to say the sequence of partial sums Sn. So limit as n goes to infinity of Sn. So for every series, we can think about convergence or divergence in this way. But I want to be upfront. Finding out the sequence of partial sums is, as a formula, is sometimes pretty hard. There's a couple cases where it's not too hard to do. This is an exceptional sequence, or excuse me, series. I'm just going to try really hard to get those right. In fact, this one has a name. This one's called a telescoping series. And the other one where it's going to be easy to find a formula for Sn is going to be the geometric series. Aside from those two cases, finding a formula for Sn is actually spectacularly hard. It's kind of an interesting mathematical problem. And that's the reason why we have all of these things. It's because of the difficulty in finding out the sequence Sn as an actual generated formula. But this is a case where we can do it, so let's do it. We're focusing on this bit right here for the moment. Sn. Sn is a summation of the sequence an as you go from 1 to n. So it starts off as an index I equals 1. So when I is 1, we're just plugging a 1 right in here. That's the end term of the sequence. We'll get 1 minus 1/2. Then we increment. We go from 1 to the next index of 2. When I is 2, we're plugging 2 inside here to get 1/2 minus 1/3. And this pattern repeats. But notice my parentheses are only here to organize. They can be dropped immediately. And there's cancellations as we go through. So if we increment to the third, index I is 3. That means we're plugging 1/3 here, minus 1/4. This pattern continues. Let's just start writing them out. Plus 1/4 minus 1/5, plus it's going to end right when we get to n. But when we get to n, it looks like this, the nth term of the sequence. So let's go plus ... Say we did a whole bunch of really hard work, and now we're at the end. 1 over n minus 1 over n plus 1. So that's what Sn would look like as a formula. And it's something that we can actually simplify too. We can cancel these two terms, move over, cancel these two terms. This is what's making it telescoping. You're getting the thing on the left surviving, it won't cancel. And the only survivor is the thing that telescopes out to the far right, 1 over n minus negative 1 over n plus 1 survives. These cancel in pairs. So at negative 1/5, it'll cancel with the next term if we wrote it down. And with this one, 1 over n, you would have canceled with the prior term if we wrote it down. Just two survivors then. So Sn is 1 minus 1 over n plus 1. So we could take that information, come back over here and write that this is equal to the limit as n goes to infinity, 1 minus 1 over n plus 1. And over here, we're just taking the limit of an ordinary sequence. The constant 1 doesn't change. However, 1 over n plus 1, this part is going to converge to 0 since n grows without bound. So this becomes 1 minus 0 for a 1, which means it's converging or convergent. So this is a kind of a rare kind of series. The telescoping sum like this one doesn't always come up, but its major purpose today is just to get a feel for what this definition right here is trying to say. If this really is a convergent series, it means we're adding together infinitely many terms of those form. There's a bunch of cancellations, of course, but when we add up those terms infinitely, we get a number, 1. What we're really saying, though, is as the index n gets larger and larger on the sequence of partial sums, that thing gets closer and closer to a 1. So we intuitively say the summation of all of the terms in this series is 1 because that limit existed. So series are weird kinds of things. We'll be spending a lot of the course dealing with them. But any questions, folks, with this first full example?
I can't be the only one that thinks it's weird that 1 over n plus 1 now converges, right?
Yeah. That's the issue with this one right here is that 1 over n plus 1 converges is only because we're taking an ordinary limit. Whereas over here, this thing diverges
Okay.
because it wasn't a limit. We were adding more and more terms altogether, and the sum was getting higher and higher and higher. But yeah, that is definitely the battle with sequences versus series. It's just kind of digesting what one is trying to say versus the other. But does that help out to think in those terms? Of series is always just adding more and more?
It does, yeah.
Gotcha. And you know, another thing we could do that helps out is on this graph right here, let's bring this back to the one where it was divergent. That's when this was power 1. So now everything updates. Oh, not everything. There we go. Everything updates on that. And let's get a little bit more graphics on this, just to highlight that incongruity between something converging, something diverging. And this is what it looks like. There's thousands of terms here, so it looks kind of funny. But AN is the one in blue. And if we plotted this way, that'd probably be a better screenshot. There we go. Let's just overlay it. So the one in blue is the sequence, and the sequence goes to 0 converging, but it didn't do it fast enough. That's the trouble. And that's why the series right here, the one in orange, just got larger and larger and larger. If we plug in just a higher power, say it's power 2, then the sequence still converges to 0, absolutely. However, the series is now converging to something close to 1.6. It's only because this time when it converged to 0, it did it really fast as a sequence, allowing the series up here to truly converge. But those are, again, the things that make this kind of topic pretty difficult to think about. Again, that's why we're trying to take this step by step. Any other questions at the moment? Okay, thanks for the questions so far. These are notes where if no one asks any questions at all, we just sort of rip through them, and that doesn't help out anybody. So I appreciate the questions. It's a way to just kind of pump the brakes a little bit and think about a problem a little bit longer. So we looked at a telescoping series. This one's kind of a one-off. I didn't ask this as a homework question. There really isn't a lot of questions to even assign on these. Its major purpose, again, is to look at that definition there. But this one's more important. I made a typo on there. I put power n, it should be power n minus one for this geometric series. Not because that's strictly required, but mainly that's because it's part of the formula right over here, power n minus one. So this geometric series does come up a lot, just like the harmonic series. This is another subclasses of series with a name, making them pretty important. What we're doing with a geometric series is we start with a value a, and then we multiply a by something called the common ratio r. That's our next term. Then we add a new term where we're multiplying by the common ratio squared, then the common ratio cubed, and so on. This is what forms up the geometric series visualized this way. It's a sum as n goes from 1 to infinity of a times r to the power n minus 1. This thing could either converge or diverge, and its convergence and divergence totally depends on r, the common ratio, how big it might be. There's another theorem that's related to this one. Let's go back to section 11.1. I'm going the wrong way. 11.1 is downwards. To think about the geometric series, we need to also think about this formula here. There it is. This sequence is the common ratio r to a power of n, but now it's just a sequence. We're not adding up terms. We're just looking at what happens to the nth term as you take a limit and go off to infinity. If r is between -1 and +1, the limit of that thing is 0. If it's equal to 1 exactly, then the sequence converges to 1, and it's divergent for all other cases. So coming back to our problem right here, we want to discover if this converges or diverges, so we'll write out, take a summation as n goes from 1 to infinity of a. This could be 5, 6, pi, anything like that. It just can't be 0 because then the problem is boring. You're adding a bunch of zeros. R to the power n minus 1. This is going to be equal to the limit as n goes to infinity of the summation as I goes from 1 to n of a times r to the power I minus 1. So essentially all I've done here is that's the series. We want to know if it converges or diverges, but we're adding infinitely many terms. That's not easy to think about in totality. So we're inching towards it. We put in a limit as n goes to infinity, where the upper end of this gets larger and larger. So we're wondering if this converges. And this whole thing right here is nothing but Sn, the sequence of partial sums. So this is the limit as n goes to infinity of Sn. If we can come up with a formula for Sn, then we can discover the convergence or divergence of this entire thing. Let me just try to highlight this in a more sensible way. Any questions so far, folks, with the write-up here? This is really just the definition of convergence versus divergence. Okay, so the next thing we're going to do is try to get a formula for Sn. Here's how we can start. Let's just write out what Sn is. It's a partial sum. There it is right here. Let's just write it out, not without the summation notation. It goes a plus a times r plus a times r squared, and so on, all the way down to the line, down the line to a times r to the power n minus 1. That's a little bit tricky on why it ended on n minus 1, but the reason for that is going this far, that's n terms. Excuse me, that is n minus 1 terms. Add the a on the very left, and we get to n terms altogether. Does that make sense to folks so far? Okay, so I think it looks a little bit weird when you write out all these terms, but you write out the nth term as a to the power n minus 1. That's just because the first term didn't start with a power of a. So we're ending up there. Then you could do some weird kind of exponent surgery to this thing. Take r times Sn. If you did that, You're bumping up the powers on everything, and so this becomes AR plus AR squared plus A to the power Rn. Let me try and make that look a little bit better as an exponent. So all I've done next is multiply this by power R. On the last term of the partial sum, we get power Rn now, if we do that. And the reason for doing all that is we need to use this information. Let's just take a screenshot since we're using it. Somehow, some way, in order to come up with the value for Sn and then to take the limit of it. So at the moment, we're coming up for the value of Sn. And here's what we do next. We take Sn minus R times Sn. So the only reason that we can come up with a quick formula with this is because the geometric series has this nice regular form. We bump up the power, we get that form again. And that means when we go to take a difference, it goes like this. A plus AR squared plus AR to the power n minus 1 minus AR plus AR squared plus AR to the power of n. And this starts to look like a telescoping sum out of nowhere because these cancel. They have opposite signs. AR squared cancels. We have a whole bunch of cancellations. AR power n minus 1 cancels. It's right there. We just didn't write that prior penultimate term there. The only survivors is A and A to the power of Rn, just like the telescoping sum. So now we've got a formula. Well, almost. Let's keep on bumping that down. We can now say that here on the left, we can factor out the partial sum Sn leaves 1 minus R to the right. On the right-hand side, the only survivors are A plus, let me try again. It's not a plus, right? It's a minus. Control Z's to the rescue. A minus that last term, A to the power of Rn. Next thing we could do is just divide by 1 minus R. But notice already, we're dividing by R by 1 minus R. We need to make an assumption. R cannot be 1. That actually might make sense though, because if R was 1 right here, what would happen? It would turn into the summation and goes from 1 to infinity of just A. When R is a 1, 1 to any power is just 1. And now this would look like this. A plus A plus A plus A. That's just a wholly uninteresting series. It's just going to diverge unless A is 0, because now you're adding together infinitely many non-zero terms whose size never ever change. They're always constant. So that seems like a reasonable assumption in the first place. R really shouldn't be 1 for this kind of series. So this is why R is not 1. Let's just convey that with a scratch work here. And we're seeing it again because if we divide by 1 minus R, we really need that assumption right here. It's now A minus A to the power of Rn divided by 1 minus R. So while we have now a formula for this, we can come back and say, therefore, the summation as n goes from 1 to infinity of the geometric series A Rn minus 1 is equal to the limit as n goes to infinity of Sn like we had before. And this is the value of Sn. A minus A to the power of Rn divide by 1 minus R. We can take that limit because when we go to take that limit, the only part that varies is that. Everything else is constant here. And we just so happen to have a theorem to help us out immediately. Theorem number 9 says, as long as R is between -1 and +1, you have that this goes to 0. It's going to equal 1 when R equals 1, but we don't even care about that case. It's nonsensical in this situation. And we have divergence for all other values of R. So let's say here for our next assumption, assume that -1 is less than r is less than 1. So we can use that row and take the limit. We get that this part right here, circled in orange, goes to 0. And this becomes a divided by 1 minus r. So we have convergence when -1 is less than r is less than 1. So that's the whole story for the geometric series right up here. So a geometric series starts off this way, but the only way to make sense of this to get a finite number is we insist r is not 1, or else we're adding a bunch of terms that never change, that has to diverge. If r is not 1, then our next assumption is now it has to be between -1 or +1. Otherwise, this value right here by the red dot diverges. It goes off to either positive or negative infinity, which would mean the geometric series diverges. So in this specific case right here, we actually have an answer. The geometric series gives you that as a total sum. That is also rare. Coming up with a total sum for a series is spectacularly hard. Some of these are open questions. For example, there's lots of common series where nobody has a formula for the total sum. We just know it's approaching some approximate value. Not too different from some of the things we've been looking over here. But the geometric series is special. It gives you the total sum right there. So that segues us to this part of the notes. With the geometric series. So the whole story about this is the geometric series converges when r in absolute value is less than 1, between -1 and +1, in other words. And when it does converge, it converges to that as the total sum of the whole geometric series. And if it's greater than 1 in absolute value, we just have a divergent series altogether. So some of these are kind of fast to do, but I feel like this might be a good spot for us to pause because our very first question here in part A has this little struggle. This is what we were doing in section 11.1 when we were coming up for a formula for the nth term of the sequence. We still have to do that because this is equal to the summation as n goes from 1 to infinity of an. And so to even get this problem started, we need a formula for an. That's not too bad, too different from what we did in section 11.1. But again, I think this is a good one to pause right here. That way we're not breaking a problem in half across an exam that we have on Monday. We'll come back to these notes, start calculating geometric series, determining their convergence, divergence, and look at this good old test for divergence right here, which is easy to misapply to finish out the notes on Wednesday's class. So I think this is going to be a good stopping point for us right here. Sorry we didn't quite make it fast enough to the first formula there. That means we get to take our time with it after the exam. Any last questions or comments then, folks, before we head off to the weekend? Okay, well, have a great weekend, folks. Again, just a reminder that we said at the start of class, if you're working on problems, studying over this weekend, don't hesitate to email me. I check my email every single morning, and I'll always clear my backlog. So even if you send me a lot of questions, I will get to each and every one of them. So have a great weekend, folks, and I'll see you all in Monday's class.